Good morning everyone. Today we are going to discuss about electromechanical energy conversion. What is electromechanical energy conversion? The basics of electrical machines starts with electromechanical energy conversion. The conversion of electrical energy into mechanical energy and vice versa, mechanical energy into electrical energy, is known as electromechanical energy conversion. Many devices uses electrical energy to produce mechanical energy or light energy, heat energy, like that. If you take a heater, it takes electrical energy, it produces heat energy. If you take a motor, it takes electrical energy, it produces mechanical energy. Many devices uses electrical energy to produce light energy or heat energy or mechanical energy. A device which converts electrical energy into mechanical energy is called a motor. Vice versa, if a device which converts mechanical energy into electrical energy is called a generator. Electromechanical energy conversion involves the interchange of energy between electrical system and mechanical system through a medium of coupling called electric field or magnetic field. There is definitely a medium is required to convert one form of energy into another form. If you take motor, if you give electrical energy as input, a medium magnetic field will be created. Or if you take another type of devices which uses heat energy, there is an electric field may be there. Hence, electromechanical energy conversion consists of three essential parts. Those are electrical system, mechanical system and coupling field. Electric field or magnetic field, any one we can use. What are the features of electromechanical energy conversion? There are so many salient features of electromechanical energy conversion. One of that is principle of conservation of energy. The principle of conservation of energy holds good for electromechanical conversion. Energy can be neither be created nor be destroyed, but it can be converts one form of energy into another form. Second thing is, while converting electrical energy into mechanical energy or mechanical energy into electrical energy, there are huge losses occurs. During the energy conversion, the losses occur in the system. Those losses are electrical losses. While if you give electrical supply for a motor, some electrical losses, that means copper losses will be takes place. Without losses, we can't transfer the energy from one form to another form. Electrical system, magnetic field, mechanical system. Finally, we are getting mechanical output. Electrical system. Electrical losses are copper losses. These losses depends on how much current the motor is taking. The current square into resistance of the winding gives electrical losses, that is copper losses. These are variable losses, depends on load current. And magnetic field. In magnetic field also some losses takes place. Those losses are field losses or core losses. Those losses also may be known as iron losses. Iron losses are two types. One is hysteresis losses and eddy current losses. Mechanical losses or friction and windage losses comes under mechanical losses. Finally, we are getting mechanical output in case of a motor. The same reversion principle we are applying for generator also. We are giving mechanical input for a generator. After that, mechanical losses will be takes place, some mechanical losses, and magnetic field, some field losses. Finally, we are getting electrical output after overcoming all the losses. How these losses appear in DC machines or any motor? If you take a motor, if after running the motor for some hours, you are observing that some heat will be observed. What is the reason why the motor gets heated? Some reason is due to friction and windage losses, and some reason is due to losses which may be appear in the form of heat. That is very important. The losses may appear in the form of heat. One thing we have to remember, the principle of conservation of energy is applicable for losses or not. The losses or copper losses or friction and windage losses or iron losses, whatever be the losses, the principle of conservation of energy is not applicable for losses. That thing we have to remember in mind. The principle of conservation of energy is not applicable for losses. That may be whatever be the losses. Now we are going to discuss about energy balance equation. Energy balance equation explains how the energy is balanced from electrical energy input to mechanical energy output, that is a motor, and also it explains how the mechanical energy is converted into electrical energy. From the figure, energy balance equation or energy transfer is given by, for a motor, we are getting mechanical output as a power. Mechanical power is the output from the motor. First we are giving electrical power input, after overcoming all the losses is coming mechanical output. Electrical power input minus electrical losses, that is I square R losses, plus field losses or iron losses, plus friction and windage losses. These losses are takes place in bearings on moving parts. Mechanical energy output, similarly we are electrical energy input minus I square R losses plus iron losses plus constant losses, that is friction and windage losses. One thing we have to remember, which losses are constant, which losses are variable. Copper losses depends on current, hence these losses are variable. If you consider friction and windage losses, constant losses these are. Iron losses also constant losses. Constant losses combines two losses we have to remember. One is iron losses and another one is constant losses. What are the magnetic properties of the materials? Flux density and magnetic field intensity, H, all these will be various parameters related to magnetic properties. The space surrounding a magnet, the field surrounding of a magnet. If we take a magnet, if it is a magnet, the space surrounding of a magnet is called magnetic field. Magnetic flux, it is denoted by the letter phi. The ratio of magnetic force or MMF to the reluctance is called magnetic flux. The ratio of one of the important definition of magnetic flux phi is MMF by reluctance. Magnetomotive force to the reluctance ratio is called as magnetic flux. The unit of magnetic flux is Weber. So consider an area A, assume that B equal to phi by A, phi equal to BA, we can cut. BA cos theta we are applying, where theta is the angle between. What is magnetic flux? Magnetic flux is the measurement of total magnetic field passes through a given area is called magnetic flux. If you consider a magnet, the space surrounding of a magnet is called magnetic field. Magnetic flux density, another definition or magnetic properties. The total magnetic flux passing through per unit area is called magnetic flux density. Magnetic flux density unit is Weber per meter square. It is denoted by B equal to phi by A, where phi is Weber, the flux unit is Weber and area unit is meter square. Magnetomotive force. What is meant by magnetomotive force? You know EMF, electromotive force, and what is magnetomotive force? It is the force or pressure which tends to move or produce the magnetic flux. Due to this magnetomotive force only magnetic flux will be produced. MMF equal to Ni, where N is the number of turns, I is the current. Whenever number of turns are increased, when current number of turns into current, that is product of number of turns into current gives MMF. The number of turns N equal to number of turns, if I is the current, the MMF depends on what is that MMF depends on current or number of turns. If you increase the number of turns, then magnetomotive force will be increases. The unit of MMF is ampere turns. Next, another property of magnetic material is magnetic field intensity or magnetic field strength. It is denoted by. It is defined as a magnetomotive force per unit length is called magnetic field intensity. It is defined as magnetomotive force per unit length. H is given by MMF to the length. MMF equal to Ni, you know that already we discussed that MMF equal to Ni. From that we can identify H equal to Ni by L. H equal to MMF by L, that is magnetomotive force per unit length is called magnetic field intensity or magnetic field strength. The units of magnetic field intensity is ampere turns per meter, because singly excited system and doubly excited system, or singly excited magnetic system or doubly excited magnetic system. The word excitation means giving the energy for something. Excitation means when you feel excitation, your energy level will be increases. Excitation, I'm excited, somebody tells that. I'm excited means the energy level will be increases at that person. The word excitation means that gives energy for something. In missions, giving the power supply from source is. In singly excited means the mission has only one source only. Doubly excited means the mission has two sources, double sources. Singly excited systems are what are the examples for singly excited systems are DC missions or singly excited systems, single phase missions are the singly excited systems. Doubly excited missions have two sources for excitation. Examples for doubly excited missions are synchronous missions or doubly excited. A singly excited system for toroid as shown in figure. It consists of a toroid. After that we are giving a supply, a DC supply for the toroid plus and minus. Hence only single supply is there. Hence it is called singly excited system. A singly excited attracted armature type relay. A singly excited attracted armature type relay as shown in figure. It consists of an armature which is moving and a core is fixed, and we are giving the DC supply or AC supply for that number of turns. Due to supply, it acts as electromagnet, it attracts the armature or movable part, hence it is singly excited system. From the figure, let us assume that the armature is held stationary by some area and current is increases from 0 to some value. As a result, more flux with flow in the system and armature attracted towards source producing mechanical energy. Motors, some devices produces mechanical energy. Those are electromagnetic relay, attracted armature relay. A relay is a device which senses the fault. After that it intimates to contactor to open. A relay contactor will be initiated by relay. Relay, how it works, all this will be studied in power system. Let us discuss. A small motion will be appear in relay due to electromechanical energy conversion. That motion, how it, what is the principle, all this will be discussed. The expression for electrical energy input and mechanical energy developed or in attracted armature relay or singly excited system. Let us discuss now. Electrical energy input equal to, consider a simple magnet system of toroid excited by a single coil as shown in figure. According to Kirchhoff laws KVL, what is Kirchhoff law KVL? The supply voltage equal to total drop, V equal to IR plus E. Let assume that the total flux linkages N phi equal to phi. Assume that the total flux linkages means number of turns into flux gives the total flux linkages, and assume that it is a lambda. The induced EMF, according to Faraday's laws of electromagnetic induction, the induced EMF is E equal to N d phi by dt. That equal to d by dt of N phi, E equal to d lambda by dt. From equation 1 can be written as V equal to IR plus d lambda by dt, where lambda equal to total flux linkages. Multiplying the equation to both sides with I dt, then Vi dt plus I square R dt plus I lambda. Vi dt minus I square R dt equal to I d lambda. If you made a common I dt, V minus IR dt equal to I d lambda. From equation 1, V minus IR equal to E, hence the equation 3 can be written as EI dt equal to I d lambda. From the figure 4, let us assume that the armature is held stationary by some area and the current is increases from 0 to some value. 0 నుంచి some value current increase అయితే ఏమవుతుంది? As a result of more flux will flow in the system. అంటే కరెంట్ పోయిందంటే కాయిల్లో ఖచ్చితంగా మ్యాగ్నెటిక్ ఫ్లక్స్ రావడం వల్ల ద బీమ్ కానీ ఆర్మేచర్ కానీ అట్రాక్ట్ అవుతుంది. అంటే రిలేస్లో ఫిక్స్డ్ పార్ట్ ఒకటి ఉంటుంది, మూవింగ్ పార్ట్ ఒకటి ఉంటుంది. As a result of more flux will flow in the system, armature attracts towards source producing mechanical energy. The incremental electrical energy is given by dW electrical equal to EI dt. By substituting those equations previously what we discussed, dW electrical equal to d lambda by dt into I dt. Therefore, incremental electrical energy equal to dW electrical equal to I d lambda. For n number of turns, incremental energy equal to dW electrical equal to Ni d lambda. dW electrical equal to Ni d lambda. From 6 and 7 equations says that to extract the energy from the system, the flux linkages of magnetic field must be changed. To extract the energy from the system, the flux linkage of magnetic field must be changed. This change in flux d lambda causes the generation of reaction EMF E. The reaction EMF sometimes in case of DC motors it is a back EMF. Let us discuss all this. Back EMF will be next DC motors topic. Flow of current against reaction EMF E causes extraction of energy from electrical system. The energy balance equation in the differential form is given by dW electrical equal to dW mechanical plus dW field. Total electrical energy input equal to change in mechanical energy plus change in field energy. Since we have assumed that the armature held stationary and small mechanical movement of relay that can be neglected. Hence dW mechanical equal to 0. When the small current is there, the mechanical energy output becomes 0. Hence dW electrical equal to dW field. Assume that one equation. dW field equal to Ni d phi, W field equal to integral, if you want total field, incremental energy in field total, if you integrated differential incremental energy over a flux, that is W field equal to integral 0 to phi Ni d phi. From that W field equal to integral 0 to phi Ni d phi. This graph shows linear relationship between MMF and phi. This is about singly excited system. When singly excited system given the supply, due to MMF only, the armature will be attracted towards the core. Discuss about doubly excited system. We already discussed in the previous section singly excited system. Single phase transformers, single phase machines are singly excited systems. What is doubly excitation? Excitation means giving the supply for something. For work, any work, if you give the supply, it is the excitation. Giving the DC supply for DC machine or DC motor, it is called the excitation for field winding. Simply giving the supply in both field and armature, then it is called doubly excited. Doubly excited means supply, two supplies are required, double supplies are required to excite the system, then these are doubly excited systems. Doubly excited magnetic field system or multi-excited magnetic field system, how it works, what is the relations, what are the equations, those will be discussed in this section. Multi-excited system is the most particularly used in DC machines, synchronous machines, loudspeakers. Let us consider doubly excited system as given below. Giving the two supplies for a machine is called doubly excited magnetic field system or the multi-excited magnetic field system. Multi-excited system most particularly used in One of the DC separately excited DC machine. DC separately excited DC machine, we require two supplies. One is for field winding will be excited from separate source, and armature will be excited from another supply source. If it is a generator, from the supply from the armature we are taking the supply. Synchronous motor or synchronous machine is a doubly excited machine. Loudspeakers also doubly excited machines. Let us consider a doubly excited system to explain. Figure shows a doubly excited system. It is field winding is excited from separate source V and armature is excited from a separate source 2. It has two independent sources of excitation, consist of stator and rotor. If you consider a synchronous machine, if you take this doubly excited system, it has two supplies. Assume that synchronous machine or synchronous generator or alternator, if you consider, the stator has armature, that is armature is supplied from a 3-phase AC source, or we are obtaining the AC voltage from the stator, 3-phase AC voltage from the stator. It has two independent sources of excitation. Consider a stator and rotor. The stator is energized from a source 1, that is 3-phase AC source or 3-phase supply will be obtained from alternator. The rotor is energized from a source 2, that is DC supply. A field is provided in the rotor of synchronous machine. That field is energized from a DC source. If you go for any power plant or alternator or synchronous generator is working in a power plant, the alternator produces electrical energy. So many power plants. In these power plants we are providing a batteries to give DC supply for alternator for excitation. The rotor is excited from the DC source. The stationary part of the magnetic machine is called stator, rotor is rotating part. The rotating part of the machine is called rotor. The MMF produced at both stator and rotor is same direction, but magnetic torque TE is in an anti-clockwise direction as shown in figure. The differential electrical energy input to a singly excited system is the differential electrical energy input for a singly excited system is I d lambda. Differential energy input from two energy sources is given by differential electrical equal to Is d lambda S plus Ir d lambda R. We are having two supply sources for stator and rotor, hence the equation will be like that, where lambda S and lambda R are the total instantaneous flux linkages of stator and rotor. S stands for stator and R stands for rotor. Hence, lambda S and lambda are expressed as in terms of mutual inductances of self-inductance. Mutual inductance and self-inductance, if you express those, what is mutual inductance, what is self-inductance, those definitions you must know. Lambda S equal to LSIS plus MSR IR. Lambda R equal to LR IR plus MRS IS, where LS and LR is the self-inductances of stator and rotor. MSR and MRS is the mutual inductances of stator and rotor. Substituting equation 2 in 1, dW electrical equal to IS d LSIS plus MSR IR plus IR d LR IR plus MRS IS. From thus, if there is no mechanical energy, then dW electrical equal to dW field. Already we discussed in singly excited system. The change in field energy is given by Is Ls DIS plus Is MSR DIR plus IR DLR DIR plus IR MR DIS. That gives Is Ls DIS plus IR LDR plus MSR DIS IR. This is the equation related to doubly excited system. This is very important for understanding synchronous generator. Basics of synchronous generator will come in electrical machines 3 or synchronous generators. What is energy and co-energy? What is energy? What is co-energy? Energy can be neither be created nor be destroyed. That is law of conservation of energy, you know that. The main advantage of electrical energy is that it can be transferred to anywhere. Any hilly areas also we can transmit electrical energy easily. But if you want to transmit a mechanical energy, it is very difficult to for some places. That is the advantage of electrical energy. There are so many advantages of electrical energy. It is a clean and green energy. It does not produce any smoke. If you give electrical energy for a device mission, if you obtain mechanical energy, it is a motor, you know that. In singly excited system, the electrical energy is the stored in magnetic field. In capacitors, the electrical energy is stored in electrostatic field. The unit of electrical energy is kilowatt hour. Energy consumed over a period of time is called energy, electrical energy. The unit of electrical energy is kilowatt hour. What is energy? The energy is the power into time, the product of power and time, or the energy consumed over a period of time, that is energy equal to integral 0 to t p into dt gives what is the total energy consumed. What is meant by co-energy? In physics and engineering, co-energy is non-physical quantity and measured in energy unit kWh, but used in theoretical analysis for a physical system only. The concept of co-energy is applied to conservative systems having linear relationship between input and stored energy as shown in the figure below. In the figure, if you consider the figure, in the figure, lambda you are taking on y-axis, that is total flux linkages, current is taken on x-axis. The OAB is the curve, OAB is the energy, actual energy we consume. For that, OAC is the co-energy. OAC is the co-energy. The graph represents energy and co-energies. Example for co-energy is magnetic co-energy. Magnetic energy we are not utilizing, but we are obtaining mechanical energy. That mechanical energy only we are utilizing. That means co-energy is used for transferring the original energy what we required. In a singly excited system, the electrical energy is supplied to system device and is stored in magnetic field. dW electrical equal to dW field, that is the magnetized equation 1. dW electrical equal to EI dt, that we discussed already previously. dW field equal to dW stored equal to I dy, we can obtain EI dt equal to I d lambda that equal to dW stored, incremental energy stored. If there is no finite change in flux linkage from one value to another value, lambda 1 to lambda 2, then if there is a finite change in flux linkage from one value to another value, lambda 1 to lambda 2, then incremental energy stored, that is delta W stored equal to lambda integral lambda 1 to lambda 2 I lambda d lambda. From the figure, the co-energy equal to area of OABO, that equal to energy stored, that equal to integral 0 to lambda I lambda dy. Co-energy equal to area of OACO, that equal to W dash stored equal to integral 0 to I lambda I di. That is energy stored in the inductor coil equal to half Li square you can obtain now. If you integrate the above equation, integral 0 to I lambda I di, we can get energy stored in magnetic field is energy stored in inductor is given by half Li square.